We're going to start with our basic geometry parts, and we're going to build up from here with some things. So we're going to start with points, lines, and planes for the first lesson today, and then we'll get into some line segments in the second part of the day. So the first thing we're going to talk about is point. The point is the basic thing in geometry. It's where you start with everything, and a point is a location. Goes in that first blank. It has no size or shape. It doesn't take up space, is what we're saying. A point is just, it's a reference point. It doesn't have any kind of size or shape, no area, nothing like that, okay? And then we always use a capital letter to name a point, okay? So for this example here, this is point A. That's the what that picture on the left is on your handout there. So that's point A. So a capital letter to use that. We tend to try to stay away from some of the letters as representatives like O. I usually avoid it. Our curriculum uses it a little bit. It's not a rule that you can't use O. I just try to stay away from it because it looks like a zero, and I don't want to confuse those things. So, but just a capital letter, and usually a print letter. Don't do cursive letters. I don't know. I think that's probably not an issue, but just script letters mean something else. So capital print letters is what we want to use there for a point. And then the next box is about a line. And a line is made up of points. We know this from algebra when we graphed lines, that line represented all of the ordered pairs on that line. So all those points out of that. So any 2 points form a line. It takes 2 points to make a line. You've heard the saying that the shortest distance between 2 points is a straight line. So that's a geometric concept. And a line has no thickness or width. Okay, so it's just representing all of those points in between those points and beyond for the picture that we've got on the left there. So when we name a line, we can name it by picking 2 of the points that are on the line. And for our example here, we've got X and Y that are labeled there as 2 points on that line. We can name it by using those 2 letters for those points, or with a lowercase script letter, which it'll look like just an italicized letter beside the pictures that you'll see here. So for this one, we would call this XY. And the way you want to note that is you put a line with arrows on each end above that. That's the notation that's most commonly used. That's what I'll use most of the time. If I say something about a line, that's the object, the line XY. Okay. And then you could also write out the word line XY or line N. And I'm going to use a script N, so I don't know how much y'all learned of cursive in elementary school. My second grader's been working on cursive. Impressed me. I didn't remember learning cursive in second grade. You may not have learned cursive much at all. But script, when we talk about that, it's going to look kind of italicized or a little bit fancier on the diagrams that you see. But again, the first notation there, that's the one I'm going to use the most. And that's the one I expect you to probably use the most as well. All right. Collinear points, that means they're on the same line. Co meaning together. So collinear means they're on the same line. Non-collinear points are not on the same line. Okay, so if I took that example on the left there, that's line XY or line N, and I wanted to get a non-collinear point, I just pick a point out here. I might call it Z out of that. So that gives us 3 points that are not all 3 on the same line. That other point is somewhere else. So the points X, Y, and Z are non-collinear because they're not all on the same line. X and Y are collinear, but X, Y, and Z are non-collinear because they're not all on the same line. It just takes one to be off the line to be non-collinear. So really easy concept there. All right. All right. The next one is a plane. All right. A plane is a flat surface. So we're building up pieces here. When we do geometry, most high school geometry is what's called Euclidean geometry, which everything happens on a plane or in three-dimensional space, which would be three planes all together. But a flat surface, it's made up of all these points. We don't, no way we can represent every point that's on there. The same way you can't represent every point or tell every point that's on a line that you graph. Planes are the same way. There's just tons of points on there, and we're just going to represent some of them that are on that plane. Any 3 points make a plane. Takes 3 points to make a plane. 2 points to make a line. 1 point is just itself. It's a location. Okay, so 2 points to make a line, 3 points to make a plane. And a plane, we may draw it as this kind of parallelogram looking shape, slanted rectangle, whatever, how you want to describe that. We're going to draw it like that, but understand that it extends in all directions. It goes everywhere. Okay, so understand that it just extends everywhere. And then when we name a plane, we're going to name it using 3 non-collinear points. And the reason we want to use non-collinear is because if we use 3 linear points, it's easy to confuse that with a line, because you could name a line with 3 points that are on the same line. You really only need 2, but so we want 3 non-collinear points. And so for this one, we would call this plane JKL, or it doesn't really matter what order you put those in. But my brain says do it in that order. And then you could also name it using an uppercase script letter, which is usually in one of the corners. It doesn't have to be in the bottom right corner. It can be in any of the corners, but they'll put like a script uppercase letter in there. So a cursive. This one, it would be plain P. And forget my cursive P's. But again, it'll look a little fancier on your diagrams than the other points. And there won't be a dot beside it, so you know it's not a point. That's the name of the plane. Coplanar points is just like on a collinear points that are on the same line. Coplanar means they're on the same plane. And then non-coplanar points are points that do not lie on the same plane. So you've got to have at least 4 points to be non-coplanar. And it kind of introduces that three-dimensional idea that if you've got a plane P here and you have a point that's not on that plane, you would pick, somewhere else. It'd be off plane there. You might call that M. And then you would be able to say M, K, J, and L are non-coplanar because M is not on that plane. So if it's not in the box, we're saying it's not in that plane out of that. So sometimes planes get a little confusing when they put more than one in the picture, and we'll see that as we get into some examples here that get a little tough. All right, so let's look at, we got a point, which is just a location. We got lines, which is just a bunch of points. And then we got planes, which is the flat surface that we put stuff on. And then what we can have is things happening where we're intersecting those lines and planes. If 2 lines intersect, we did this in algebra, what do they intersect at? A point, one single point, if they intersect. And remember, lines don't have to intersect. They could be parallel. They could be what's called a skew line, which they don't intersect and aren't parallel either. 2 planes, when you have 2 planes, like 2 pieces of paper, and they intersect, what does it form? Look at our picture here. What's that kind of darker thing in the middle that has the K beside it? A line. So when 2 planes intersect, it forms a line. good examples of planes that I'll use this example a lot throughout the semester are the walls. They're planes, they're flat surfaces. The corner of this, when this plane meets that plane over there, that corner over there, that seam where the two walls meet together, that's a line. So when two planes meet together, it's going to be a line. Three planes, if you had three planes meeting together, that'd be like this wall, that wall, and the ceiling. And we look up there in the top corner, what is that? Where the three planes intersect. 1 point is that very corner right there where the ceiling meets the two walls. So different things can happen there with three planes, but it gets a little more complicated when you get into three planes. But with two planes, they're going to intersect at a line, and you would be able to name that line either with points or by the script letter here is the way that they're naming that on this picture. So it intersects at line K. So now, on the back, you should have some practice problems. These are going to be our examples that we're going to talk about. So what we're going to be doing here is kind of taking some diagrams and building pieces through it, and we're going to learn some of our notation as we're doing that. So notation is a very important thing in geometry. If you put down something as an answer and it's not got the right notation in it, you really meant something else by not doing the correct notation, because just writing YX doesn't necessarily mean line YX. It may mean that segment out of that. So notation is an important thing. So as we're going through here, pay close attention to notation, and I'll try to mention it as we go along. So use the diagram at the right to answer the following. So part A says 4 collinear points. We need 4 points that are collinear. H, N, K, and I. So up here, the only line that has 4 points named on it is coming from line R. So H, N, K, and I. And it doesn't matter what order you put that in. I'll just put it in the order that we got there. Usually you'll go in order as they flow on a line in that order, but it doesn't necessarily, it's not technically required that they go in order that they're on the line at. But really easy. But because they're points, they're just one single capitalized block letter. All right. B part says a line that contains point M. Okay, so how would I do that? What's the notation that I use? That works. That's one way to name that line. What would be another way to name that line? Line P. And what was the other way? I heard somebody. There's another way. We got MO. So it'd be NO, right? You could rearrange the letters if ON and OM would be the same thing. It doesn't really matter what order the letters in. I tend to go left to right just because that's logical, makes sense to do that way, but it's not necessary that you have to do that. It's not a rule. Okay, so there's 3 different ways to name the same line from that diagram, all of which would be correct because they all contain that point M. All right. C part says a line that contains points H and K. So, yeah, HK with a line over it would be great. What's another way? Line, which one? R. Line R. Another way to name that line. Line HI. And you could do NK, you could do KI, you know, a lot of different ways to name that line. You see the idea that there's some redundancy in when we got more points on a line of different ways. So, you know, dot, dot, dot there. There are other ways to name that line, but we know which line we're talking about. And then D part says another name for line Q. JL. And make sure when we're talking about the line JL, we use that object with the line above it with the arrows on both ends. Make sure you got arrows on both ends because it doesn't mean the same thing when you have just a line above it with no arrows or with only one arrow on each end. There's other things that happen, so you got to be careful. So there's one way of naming that. What would be another way? KL. Or you could do JK, right? All right. E says the intersection of lines P and R. P and R. What's the intersection of that? Point N. And we can just use that block capital letter. We know that we don't even have to write point beside it because only one block letter capitalized means that's a point. Our notation tells us that. So pretty easy stuff. It's just a lot of informational stuff this first section. Use the diagram at the right to name the following. And look at our picture here. What do we have in this picture? We have a plane. So we see that slanted rectangle, that parallelogram shape. And then what else do we have in there? How many lines? Two. All right. We have this line that's slanting here, and then we have this line right here. What are they trying to show us? It's going through the plane, so it's like the plane is here, and it's like sticking through it like that. That's what they're trying to show there. So a lot of times it's just figuring out. Anytime you see a dashed line like that, they're trying to show it's behind it or it's three-dimensional. So be careful of that when you're reading these diagrams, because sometimes what we see, we're trying to represent something in 3 dimensions on a 2-dimensional piece of paper. So it's really hard to draw sometimes. So be careful of that. All right, so let's try to answer what's going on here. The line containing point F. All right, that would be one way to do that. Or line J or EF or DE, all of those ways of naming that line, we could do that. Absolutely wonderful way to do that. Another name for line K. BC would work. Could be EC or BE. Any of those letters there would wonderfully describe that. C, a plane containing point A. Plane M. And again, capital that. What would be another way to name that plane? Say again. AFD, yes, that would work. What letters could you not use when naming that plane? B and C, because they are non-coplanar there, because they're representing above the plane and below the plane. So you can't use B and C. But any combination of the 3 of the other 4 letters in the picture, you can use to name that plane. If they've got the script letter in the corner, that's the easiest way. But remember, you can name it by using 3 of the points on that plane. D, an example of 3 non-collinear points. Non-collinear points. B and C are 2 of them. And then I think A would be a good one. Well, B and C are technically collinear. I think D would. As long as you're including one of the non-coplanar points, you're going to be okay. Because technically, we could draw a line between A and D, but we could not draw a line between A, D, and D, all 3. So we've got to have 3 for this, a non-collinear out of that, because they don't make a straight line. A and E together is collinear, but just any 3 that are not on one of not D, E, and F or B, E, and C. Any other 3 would work. Any combination of the three. E, the intersection of plane M and line K. Point E. So intersection of a line and a plane is a point out of that. So really easy to look at there. All right, let's go on to the next one. That weird looking picture there. So what do we have in this picture? No. I agree that there are some triangles. I agree that there's a plane. That's not the only thing. There's a pyramid there, which has what? What do pyramids have that we break them down?
Square base.
They got a square. That's got a square base, or well, rectangular base. We're not sure if it's perfectly square or not, but it looks square in the picture there. So might assume that that's what's going on for this one. What else? Triangular sides. So it's got sides to it. So what do those sides make? Planes. Because triangles have how many points? Triangles have how many points? 3. Three vertices for triangle. Another name for corners. And how many points does it take to make a plane? 3. So for each side of this pyramid, back side and then this side and then the bottom, or the bottom is actually on this plane R, we get another plane in there. So there's a lot of planes in this picture. It's hard to, sometimes you don't recognize that because you see a shape and we don't recognize, hey, that shape is 3-dimensional, so it has faces, and those faces are considered planes. So part A says 3 coplanar points. So we just need 3 points that are on the same plane. A lot of options for this one. So Y, X, and V, perfect. That'll work. Y, X, and V are all on plane R, so that would be coplanar. What would be another option? X, Y, and Z. They're all the kind of the back side of that pyramid shape, and they would make coplanar as well because they're on that face. You could do Z, W, and X for this this side over here. That's a plane. You could do V, W, and Z for this side. You could even do W, X, and Y for, they're all on plane R. A lot of options for that. So there's a lot of, still correct answers that you could do for coplanar points. All right. B says a plane containing point X. So several options. I think the most obvious option is what? Plane R. That's the most obvious one because X is on that plane. The intersection of plane R and plane ZVY. Line VY. And since that line doesn't have arrows going out on it on each end, we're going to put a segment mark above it, which is just a bar with no arrows on the ends, because that line in our picture doesn't have arrows on the ends of it. So we've got to say, okay, let's only that segment there because that plane shows stopping points there. How many planes appear in this figure?
6.
All right, where are you getting 6?
If they're each side of the pyramid.
Okay, but what do we know about the bottom side of the pyramid? It's already on what plane? R. So it can't be you can't be a plane inside of a plane. So if you're already sitting on the floor, then you're on that. That's the plane you're on. So if you count all the sides of the pyramid, so the front side, back side, that's 4, and then the bottom part's already on plane R, so that's going to just be 5. I see where you're getting 6 because you get all the plane R and then the bottom of the pyramid too. But the bottom of the pyramid, since it's already on plane R, we don't count it again. So 5 would be the right number. How many planes contain point W? 3. Which ones? Yeah. VZW, XZW, and plane R all contain the point W. 3 out of that. Any questions about so far? Sometimes I always think that art and geometry kind of go together because you got to be able to see a little bit of spatial sense, and most people that are pretty good at art have a pretty good spatial sense. So sometimes they see things in the geometry a little easier than others do. But it's nothing you can't learn to do. It's not too bad. All right, so we got a weird looking diagram here. It says use a diagram to write the name of the following. So the intersections or intersection of line L and M. Point E. Good. Another name for plane Q. GFI, that would work. Are points D and E collinear or coplanar? Collinear, but not coplanar. Because point D is on plane P and point E is on plane Q, so they're definitely not coplanar. Collinear they are. D, how many times does plane P and Q intersect? Plane P and Q. They don't, because the planes are going to extend in all directions this way and upward. So the point or plane P extends this way and this one extends this way. Look at the diagram there. They look parallel, don't they? Like parallel planes. It's kind of like this wall and that wall. They never intersect one another. There's a connection between them with that line, but the planes themselves never intersect. So that would be 0 times out of that. All right. So naming points, lines, and planes, the notation stuff, kind of picking up some of that as we go along here. So not a crazy hard thing to do. So let's go ahead and do the next set of notes here, and I've got a packet or a page for you here. It is not a packet, it's just a page. It's a pretty short lesson today. Hang on to those. You'll need those to look at and do in practice. Okay. All right, I get to do a little algebra in this section, so I'm excited about that. I like doing the algebra stuff. All right, so we're going to talk about segments in this lesson. So this is lesson number 2, segment addition. Technically, there's a postulate, and in geometry, a postulate is a rule. Okay, this is something that has to work this way. Another name for postulate is axiom. There's one and the same. Postulates and axioms are rules that have to work for the world of geometry to function. Okay, it's kind of like some of the rules with regular numbers, the order of operations and things like that. Those are rules that we have to follow for things to work out the right way. So a postulate here is something that has to be that way for things to work the right way. So measuring segments, we're going to be dealing with segments on number lines. We're not really going to measure with a ruler today on segments. We're just going to use some number lines and then use some algebra to do some measuring with segments and addition and stuff. The distance between 2 points, A and B, can be written as the length of AB. And if we're dealing with a segment, it's going to be just a straight bar over the top. If we're talking about that length and not the object, we take the bar off. We're talking about a length, not the actual object. We take the bar off of it and just use AB. Well, AB with no bar over the top of it represents the length of that segment. AB with the bar over the top of it talks about the actual object. Okay, so that's a big difference when we start doing proofs later on. That comes into play because there are steps in a proof where you have to stop talking about the object and start talking about the measurement of the object. So measurement of the object takes the little picture off of it is what basically the way I look at that. So we look at that picture over on the right hand side there. How long is segment AB? How many units long is it? 1, 2, 3, 4. That's okay. So 4 units long. We don't have inches or centimeters here, so we're just dealing with units on a number line. So it's 4 units long. So the length of segment AB is 4. We would be able to say that AB is equal to 4, like the notation on the right says. Again, object has the bar, length, talking about the measurement of it, you don't have the bar. Okay. Congruent segments, if AB is equal to CD, then the segments are congruent. So that says the length of AB is equal to the length of CD. That's what the first blank says. Okay. Then the segments are congruent. And if you're going to write about segments being congruent, we're talking about the objects. So we're going to say object, segment AB, and segment CD. And then we're going to get the congruence mark here. Congruent is an equal sign, and then you put a little squiggle over the top of it. It's called a tilde over the top there. It's an equal sign with a little wave over the top of it. That's the congruent symbol. You can say objects are congruent. You can't say objects are equal. Objects are never equal. They're either congruent or not. Lengths can be equal. So measurements can be equal. So if we're talking about objects and we're saying that they're congruent, then you've got to use the congruent symbol out of that. And if we look at our diagram over here on the right, we see AB there it's 4 units long, and CD is 1, 2, 3, 4 units long. So those two segments, they're not at the same place. They might not even be coplanar here. Doesn't really matter. They're the same length. So we can say that those segments are congruent to one another because their measurements are equal. Okay. So congruent symbol, make sure you know that. That's an important one that's going to get used quite a bit. All right. So the segment addition postulate, that's the whole thing that makes this wagon roll down the road here. So A, B, and C are collinear points, and B is between A and C. All of that first part of the statement before the comma is just describing the picture that's on the right. They're saying A, B, and C are collinear points with B between A and C. All right. Then what the segment addition postulate says is that you can take segment AB plus segment BC, and guess what segment you get? Not ABC, but AC. I only need 2 points out of that. Okay. So we can add the lengths of segments and get a larger segment put together. So segment addition postulate says you can put those two smaller segments together to equal the larger one that they're included in. All right. Now, let's look at some examples of using that. So this is where just some basic stuff comes in. We're going to use this same diagram for number 1 and number 2. So over here on the left, they've got a picture drawn. They've got points P, Q, and R are collinear with Q between P and R is what the description of that would be. And it says if PQ is equal to 9 and QR is equal to 28, find PR. And notice that none of those have the segment bar over the top of them. So they're only talking about the lengths of them, not necessarily the objects. Okay, so we know PQ is 9 and QR is 28. Absolutely all you do is add them. And that would be 37, yeah, 37 equals PR. And that's our, okay. Now, on number 2, it says if QR is 17 and PR is 21, find PQ. All right, so we should be adding PQ plus QR to equal PR, right? That's what this segment addition postulate would say, right? So we would replace the things that we know and then we do exactly what you said, you subtract them. But this is where the algebra comes in. And the reason I write it out like that is because when we do proofs later on, you're going to have to write it out step by step like that. So if you'll get in the habit of doing that now with the notation and all that stuff, it will help you remember to do that when you're doing your proofs. Because if you don't do that in your proof's wrong. Okay? So PQ would then equal how much? 4. All right. Okay, let's look at a little bit more fun stuff, a little more algebra. It says EG is equal to 71, find the value of X. So we've got a segment drawn there with EF and FG, and they've gotten the pieces above that labeled, as to how long those segments are. So what's the equation that we set up? Right. So what your original thing is EF plus FG is equal to EG, right? That's what the segment addition postulate says. And we know that we're going to replace each of those things, and we would do exactly what she said. We'd have 8x minus 17 plus 5x minus 3. But on this one, we know that EG is 71. So there we have a algebraic expression with some like terms in it, and we just solved that. No 7th grade math problem. It's be 13x minus 20 equals 71, and then you would add 20. 13x is equal to 91, and then divide by 13. Seven. X is equal to 7, and that's all it asks for. Be careful when you're doing your problems because sometimes it will ask you to find X, and sometimes it'll ask you to find the measure of one of those smaller segments. So finding X may not be the end of the problem. It is on this problem, but be careful that they may ask you to find a segment piece out of that, like example 4 does. So example 4, we got TV is equal to 14x minus 8, and they want us to find TU out of that, not just find X. They want us to find TU. So let's set up the problem. So it should be TU plus UV is equal to that. Hey, come on in. Here's what we're working on now.
Thank you.
And then this is what we just finished. Yep. And then that would equal TV. All right. And then we're replacing the parts we know about. We know that TU is 9x plus 2. We know that UV is 5. And we know that TV is 14x minus 8. So we're just replacing those parts. And again, I'm being particular about writing out that extra step at the beginning just because I know where we're headed with proofs. And that's one thing that I've always found frustrating is folks leave out that step in their proofs, and it can't be left out. And then we just solve that equation. Nothing too strenuous about that. That'd be 9x plus 7, and then work it out. So subtract 9x, add 8. 15 is equal to 5x, and divided by 5, and x is equal to 3. But that's not the answer they asked for. What did they ask for? You're right. We got to plug in the x into this piece so that we can find TU. TU is equal to 9 times 3 plus 2, which is going to be 29. That's the final answer we're looking for there. So be careful. Finding x is what we've always we've stopped at with algebra. With geometry, they've got another step that they might be throwing at you. So you just got to be very attentive to detail with that. It's not hard at all. It's just formality. All right, let's look at example 5. JL is 5x plus 2. Find JL, the length of JL. So what do we do? Write out that thing. So what would that thing be? Good. And then replace everything you know. 27 plus 3x minus 1 is equal to 5x plus 2. Excuse me. Be careful not to miscopy the problem. I almost did. Just be careful about it, because the math we're doing is not hard. Most of the math you'll do in geometry is not hard. Just easy to make mistakes. So combine like terms, we got 3x plus 26 equal to 5x plus 2. And subtract 3x and subtract 2. 24 is equal to 2x. 12 is equal to x. That's not what they want. They want JL. That'll be 62. Pretty easy stuff there so far. Let's do number 6 there. CE is equal to 7x plus 4. Find the value of x. So this one is a little more complex equation, but still pretty easy solve. So again, what's our first line? CD plus DE is equal to CE. So it's that segment addition postulate part. I want you to write that first when you're showing how to set them up. And then 7x plus 4 is what's going to go in the place of CE, and then the x plus 3 plus 8x minus 9 is equal to 7x plus 4. Combine your like terms. Pretty boring stuff here. I got x equals 5. Is that what y'all got? That's the final answer on this one, because it asked us to find what x was. Didn't tell us to find a certain piece. So really easy thing. Okay? Not hard. A little bit more lengthy problem here, just because you got to find each individual piece. with this one, but that's just part of geometry. A lot of times they want you to take a diagram and solve the entire thing. And then this one, they don't put the parts on the picture, so you've got to be careful about where you put things. So if SK is 13x minus 5 and KY is 2x plus 9 and SY is 36 minus X, find each value. So my simple mind wants to do this. And then set it up, SK plus KY equals SY. And then solve it from there. So nothing too strenuous there. Just be careful that you don't put the wrong piece in the wrong place. So that'd be 15x plus 4 be 16x equals 32 and x equals 2. So if x is equal to 2, SK would be 13 times 2 minus 5, which would be 21. KY would be 4 plus 9, which is 13. And then SY would be 36 minus 2, which would be 34. And the check here is to make sure that the two smaller pieces add up to be the same as the larger piece. So 21 plus 13 is 34, so it works there. That's nice. So nothing too strenuous about the work we're doing today. Really easy stuff to start with. All right, let's get to the midpoints. The midpoint of a segment is a point that divides the segment, so midpoint, into two congruent segments. Excuse me. Okay, two congruent segments. A line, ray, or segment that intersects a segment at its midpoint is said to bisect. That's the geometry word. B-I-S-E-C-T, bisect the segment. And it's called the segment bisector. We will do a construction day with this unit kind of sometime next week probably. I'll break out the compasses and I'll show you how to bisect the segment using a compass that you can take any piece and cut it in half and create an angle or a segment bisector. Pretty neat thing. All right. So in our diagram over here, point out some notation. You've got the larger segment is segment AC, right? The point B is the midpoint. Okay, so point B is the midpoint of segment AC. And line, I'm going to call this line L because I don't have any other points on it. And that's a kind of a script L down there. And is a segment bisector of segment AC. Notice it says a segment bisector, not the segment bisector. There are multiple segment bisectors that could happen with that particular segment.
Okay, so why are you just putting the lines on instead of not the arrows?
Because look at our drawing. It has points on the ends and doesn't have arrows on it. So that is what makes it a segment. That's a good question. Absolutely important there. Because it has dots on the ends and not arrows, we're putting just a line above, just a straight line above it. If it's a line and it continues, then you've got arrows. Technically, you can't find a midpoint of a line that continues out because you don't know if it's ever going to put arrows on it. Now, on the notation wise, look at the picture. You've got these little lines in each segment. That's not a copy problem or anything like that. That's notation for congruent segments. That segment AB is congruent to segment BC, and they put those little lines in the picture. Those two segments are congruent to one another. If there were more segments in there and different segments were congruent to each other, they might use 2 lines to pair those up, or 3 lines to pair up another pair. So the little lines on segment AB and segment BC note that those segments are congruent to one another. And because those segments are congruent to one another, we know that B is the midpoint. Because B is the midpoint, it makes those segments congruent to one another. So all that is kind of recursive, and it goes around and around, and it works there. So let's look at some problems and what we can do algebraically with geometry using this midpoint idea. So if Q is the midpoint of PR, then find the value of X. So if Q is the midpoint of PR, we know that PQ is what to QR? Congruent. So equal sign with the little squiggle above it. That's the congruent symbol. And because the lines or the segments are congruent to one another, what do we know about their measurements or their lengths? That they're the same. So we could take the hats off and say PQ is equal to QR, right? So this is the geometry part. We're going to do the algebra next, but the geometry part is the object statement and then the measurement statement that allows us to do the algebra part. In the history of math, geometry came first. So when we're doing problems, I'm trying to kind of model doing the geometry part first, and then the algebra part backs that up. Okay, so we're going to set up the equation then. PQ is equal to QR, so 7x minus 16 is equal to 4x plus 2. If you'll get in the habit of at least thinking this way, when we go to do proofs very soon, you won't have any problems with proofs, because this is, other than the reasons that that happens, it's almost a proof right there. So then we solve that equation. So really easy stuff. Subtract 4x, add 16. That'd be 3x is equal to 18, and x is equal to 6. And they only ask us for the value of x, so we're done. Easy enough. Let's look at 9. If H is the midpoint of GI or segment GI, then find GH. So if H is the midpoint, we know that GH is congruent to HI, and that would mean GH is equal to HI, and that would mean that 5x plus 2 is equal to 9x minus 10. So again, the geometry statements are the congruent statement and then the equal statement, and then the algebra backs that up. And we're going to solve this for x. I'm going to add 10 and subtract 5x. So it'll be 12 is equal to 4x. X is equal to 3. But what do they want? GH. So what do we do with that 3? Plug it in. So GH equals 5 times 3 plus 2, which would be 17. Easy stuff, right? Look at 10. See what you do about 10. 2x plus 16 is QR, and then 5x minus 17 is RS. It says R is the midpoint. I have to tell us that. of QS, and then they want us to find QS, not one of the segments, the smaller segments, but the whole segment. So, what are our steps? Ooh, I know. Thanks for volunteering, guys. QR is congruent to segment RS. Because of the midpoint, they told us that it was the midpoint. That's how we know that's happening. And that means that QR measurement is equal to the measurement of RS. That's the geometry part. The algebra part, you guys got. That ain't the problem. The geometry part, I just want to drive that home, that you need to make sure that you're paying attention to the geometry part, because a lot of times we get in such a hurry because we know how to do the algebra that we will skip doing the geometry parts, and that's the whole point in this course, is the geometry parts. All right, so solve that. Excuse me. It'll be 31. Back that up. 33 is equal to 3x. So x is 11. And they want QS. What's the easiest way to get QS? Do I have to do that? I could just find one of them and then do what to it? Double it, yeah, times it by 2. Both work. It doesn't matter which way you do it. I think Tilly's saying plug it into both of them works. That might be a better way to check to make sure it's the right answer, because if they don't both end up being the same number, then you know something's wrong out of that. But I think shortcut wise, I would just plug it into the 2x plus 16 and work that out. So 2 times 11 plus 16. 22 plus 16 is 38. And then double that. 76. And I forgot to write what that's equal to. Equals QS. The length of QS is 76. Number 11 is very much the same size, same thing. But one key difference there is that they give you FH on this one. Do you have to use that? So let's look at number 11. It is a little bit different, because when you look at it, it says G is the midpoint of FH, or segment FH, and FH is equal to 6y plus 2. But then it says find y. What's different about this problem compared to the others? Yeah, it's 2 different variables out of that. So how can I find y for this problem? Might give me a plan. I think we can all do this, but I need a vocal plan of how we would do that. Okay, find x for the segments. So how would we find x for the segments? Like exactly what we've been doing. So FG is equal, or is congruent to GH. Then FG is equal to GH. And then we set that up. 4x plus 3 is equal to 7x minus 12. That'd be 15 is equal to 3x. X is equal to 5. So we found x. And then what do we do with that to help us find y? Okay, plug it in to 4x plus 3 and 7x minus 12. Do I have to do it that way? Or I could just double one of them. It doesn't matter. Either way, it's fine. So if I plug it into both of them, I'm going to add them together. If I just plug it into one, I'm going to double it. So the 4x 4 times 5 is 20 plus 3. So I'll just write that out. Is 23, and then I'm doubling that. So 46. What's 46? What's it equal to? FH. Okay. 46 is the length of the whole segment, the whole picture. Right? Now, what else do we know is equal to FH? 6y minus 2. And so that means we can set up 6y minus 2 is equal to 46. And now we got an equation that only has the y in it. So the right plan and way of going about it here. So add the 2 and then divide by 6. And that'd be y is equal to 8, right? All of that stuff to get y is equal to 8. But again, you got to have a plan and don't neglect the geometry to get to the algebra straight away. Okay, so